This is the center with the point of rotation. And let's call this again point A. So this was where it was initially. So let's draw a line from the point of rotation to where this was initially. And this is where point A ended up after we rotated the star. And we can measure this angle. So if we draw a line from the center of rotation through the initial position, and we draw a line from the center to the final position, we can measure this angle, and it turns out to be something like 36 degrees. Now let's look at this point. So this was where point B was initially. This is where point B ended up. And if we measure this angle, we find again 36 degrees. So even though point A and point B are at different distances from the center of rotation, if we look at the angle through which this disk rotated, we find that point A and point B rotates through the same angle. So we find some sort of common quantity giving me an idea of how point A changed its position and how point B changed its position, and that quantity is this angle over here. And we find that this angle is the same for any 2 points on the disk. So for any point, I replace this. So for any point that I choose on this rotating star, if I rotate that point through a certain angle, all the other points on this star rotate through the same angle as well. And that now gives me some idea or a hint about how we can start to describe this motion. We are going to think in terms of what's called an angular position. Now the angular position here, we could say initially, let's take this as like a reference axis. So we're going to use this as a reference. So if this line is just the line we're going to use as a line of reference, we can say that the initial position, angular position of point A, was at 0 degrees. And we can say that the final position, or the angular position of point A, was at 36 degrees. So instead of using a point of reference and looking at how far we end up from that point, we now have some sort of line of reference, and we look at what the angle is that is swept out by this rotation. And this we just call our angular position. And we can look, for example, at the initial position, the initial angular position of point B, still using this as our line of reference, so we can quickly measure that. So initially, so that's 71 degrees. And then the final position of point B is 106, 107 about. So this was the initial angular position of point B, that's the final angular position of point B. And if we now want to figure out what the change in the angular position was, so we're going to define the change in the angular position as being the final position of a point minus its initial angular position. We get that this is 107 degrees minus 71 degrees. which just gives us 36 degrees. And if we do the same for point A, its change in angular position is the final position of point A, angular position minus the initial angular position of point A. And that's 36 minus 0, so this is 36 degrees. So if we look at these angles that is swept out, we find that we can choose a point and we can define the change in position. But now we talk about an angular position specifically. So we're thinking about an angle that is swept out as this disk rotates. That seems to be the same for every single point on this disk. And that is now the foundation on which we're going to build our description of rotational motion, is this idea of an angular position. Angular position meaning it's got something to do with an angle that is swept out during a pure rotation.